All right, so let's get started by talking about how to find the inverse of a 2 by 2 matrix. And I have a generalized example for us here. We have a matrix A. It's 2 by 2, just like the matrix in the example we talked about in the last topic. And I'm using letters A, B, C, and D. I'm using lowercase so that we don't confuse it with our uppercase letters like we have here with capital A. But I'm using lowercase letters so that this can be generalized to any example. So you can imagine, this could be 3, 2, 1, and 0. Or it could be 5, 10, -3, and 4. It doesn't matter what the numbers are in here, as long as it's a 2 by 2 matrix. This process for finding an inverse is going to work. Now, obviously, there are many other types of matrices, many other sizes, they're not all 2 by 2. And we'll talk more about that in a later section, but for right now you only have to worry about 2 by 2. I also want to note, just in case in the last topic when I used this symbolism, A inverse, that's what this means again, A inverse. If you recall from our previous lessons in class, we talked about finding inverse functions for, let's say we had f of x, and then when we found the inverse we called it f -1, like this, x, and that meant f inverse. Well, the same terminology works here. So I am throwing that in here. I probably should have noted that in my first explanation, but just in case that threw you off, remember that's just code for inverse. Okay, let's now talk about how to find an inverse. There is a formula for this, and first I'm just going to give you what the formula is, and then I'll kind of show you where those numbers come from. So for a 2 by 2 matrix, A inverse is equal to the fraction of 1 over AD minus BC. Now I'm getting those from the element values here, the 4 element values, times a 2 by 2 matrix D and A and -B and -C. And that is our formula. Now before you panic, because that just seems so random, like where on earth did they come up with those numbers, let me tell you. First, let me get a different color here. This fraction at the front, 1 over AD minus BC. AD minus BC is something when we talk about matrices, we have something that we call the determinant. And the determinant is the value AD minus BC. And that comes from the diagonal. So A times D is on the first diagonal minus B times C. Those are the elements on the other diagonal. And that number, as long as it does not equal 0, tells us, it determines for us whether or not there's an inverse to this matrix. So a matrix has an inverse if and only if the determinant does not equal 0. So it has to not equal 0 in order to have a matrix. So we call it a determinant. It's something that gives us information. So AD minus BC, we get that number again from the diagonals, A times D and B times C. Next, if you notice over here, the pattern is that each element is switching in one way. So, and it works along the diagonals. So looking at this sort of left-right diagonal that we have here, A and D, the first thing that switches is the position of A and D. So D moves to where A was and A moves to where D is. So that's how you find the inverse on that diagonal. On the second diagonal here, the positions stay the same. See, we have B, C, and we still have B, C, but this time we switch the sign. So if these two are positive, they both become negative. Or if these two were negative, they would both become positive. So the sign of the numbers on that diagonal switch their value negatively, negative to positive, or positive to negative. So that's where those numbers come from. Now let's actually look at this with I'm just going to erase this, It doesn't erase very quickly. Sorry for the long erasing. Let's look at an example of how we would get an answer here. So we'll go back to, let's use pink because it's kind of bright. Let's say that we have our matrix from our example problem, which actually, what was my example? My example problem. Did I leave that somewhere I can find it? I did. Okay. Let's use 3, 4, and 2, 3. So this was actually matrix A in our example earlier, so it's kind of a nice example to try to find the inverse. So the way we do this first is we figure out what that first fraction is. So it would be 1 over AD, that's 9, minus BC, that's 8. So 9 minus 8 is 1, so this is really just 1 over 1. So I'll replace that with 1 over 1, which is just the number 1. So that's actually not going to change our matrix at all. Okay, next we want to take this first diagonal and we want to switch places. Well, in this case it's actually kind of easy because they're both 3. So 3 and 3, they move places, but you can't really tell because they're the same number. And then on the second diagonal we switch the sign. So 4 becomes negative 4 and 2 becomes negative 2. Now we would need to multiply everything by this fraction, but since it's 1, it doesn't really change anything. So we get an answer that the inverse of A is just the 2 by 2 matrix, 3, negative 2, negative 4, 3. Okay, so before we finish this recording, I want to just quickly talk about how we can check our work to make sure that we did the we figured out the inverse matrix correctly. So I have what we found for A, or what we knew was A, and also what we found for A inverse. Now in matrices, or when we talk about matrices, I should say, we have something that's called the identity matrix. And for 2 by 2 matrices, it's something that looks like this. If it was like a 3 by 3, any kind of square matrix can have an inverse, and it always has 1s in the diagonal, and then the rest are 0s. So inverse matrices are basically like multiplying by 1. So if I took a number 3 times 1, I just get 3. If I took a number 10 times 1, I just get 10. We know that. That's basic math. An inverse matrix is the same way. If I multiply by an inverse matrix, nothing happens. It's just like multiplying by 1. So if I have a matrix and a potential inverse, I can check to make sure that they really are inverses of each other by taking A and A inverse and finding out if they become the identity matrix. So here's how we would do that. I'd take A inverse, which is, here I'm just going to make a little line here so we don't get confused. 3, negative 4, negative 2, 3. And then I take my matrix A, 3, 4, 2, and 3. And I multiply them. That's all we have to do. So let's use a different color. And we do rows and columns, remember? So here's row and column. Now, by the way, I know that my answer matrix is going to be a 2 by 2 because I can use, we know this dimension is 2 by 2. This is 2 by 2. So looking at the outsides, we're going to have 2 by 2 matrix again. Alright, so let's see what happens. Rows and columns, 3 and 3, pairing them up. 3 times 3 is 9. Negative 4 times 2 is negative 8. So 9 and negative 8 is 1. Okay, next position is row 1, column 2. Pair up those elements. 3 and 4 is 12. Negative 4 times 3 is negative 12. 12 and negative 12 make 0. So far, so good. Last position would be second row, first column. Pair them up. Negative 2 and 3 is 6. 3 times 2 is positive 6. So negative 2 times 3 is negative 6. 3 times 2 is positive 6. Add them together and you get 0. And then last but not least, negative 2 times 4 is negative 8. 3 times 3 is 9. And so I get negative 8 and 9 is 1. And so there we have it. We got A inverse times A is equal to the identity matrix. We can also just call I. So that's a nice little check. We did it correctly.